Okay, in this video, we're going to be solving this system. And so just like with the previous ones, we're going to start by finding the eigenvalues and the eigenvectors. So to do the eigenvalues, we want to find where this determinant is equal to 0. And this is equal to lambda minus 3, lambda plus 1, plus 4. Okay, so what's going to happen is going to be lambda squared minus 2 lambda minus 3 plus 1. And this is just lambda minus 1 squared. And when we set that equal to 0, we see actually there's only one eigenvalue. So lambda 1 and 2 are both equal to 1. So we say that this eigenvalue has algebraic multiplicity 2. Okay, now to find the eigenvector, we're going to solve the equation 3 minus 1 minus 4, 1 minus 1 minus 1 times xy is equal to 0 and 0. So notice the top equation just reads 2x minus 4y is equal to 0. And the bottom equation reads x minus 2y is equal to 0. Again, the top equation is 2 times the bottom equation, so this tells us that we've done something right. And so the solution, we could say x is equal to 2 times y. And so any vector, except for the 0 vector, where the top entry is 2 times the bottom entry, is going to be an eigenvector. So any vector of this form for any parameter s is going to be a solution to this system, and as long as s isn't equal to 0, it's also going to be an eigenvector. So we'll just take the eigenvector to be equal to 2, 1. Okay, now remember, we need the theory that we talked about in class depended on us having 2 linearly independent vectors, where we could write every other vector as a linear combination of those vectors. But we only have one now. And if you remember in class, when we dealt with this problem, we had to introduce the concept of a generalized eigenvector. You know, see the class video for the theory, but a generalized eigenvector is the solution to this equation, m minus lambda I w is equal to the eigenvector. Okay, so W is a generalized eigenvector. Okay, and so with that notation, the general solution is C1 e to the lambda t v plus C2 e to the lambda t, and now we're going to multiply this by tv plus w, where again w is this generalized eigenvector. Okay, and again, watch the video from lecture if you want to go over the theory, but this is the formula that we're going to use. Okay, so we need to find that generalized eigenvector. So the equation that we're going to solve is very similar to the eigenvector equation, except instead of having a 0, 0 on the right-hand side, we're going to have the eigenvector on the right-hand side. And so we'll have 3 minus 1 minus 4, 1 minus 1 minus 1 times xy is equal to 2, 1. And notice the top equation reads 2x minus 4y is equal to 2. And the bottom equation reads x minus 2y is equal to 1. Again, notice that the equations are multiples of each other. And if they're not multiples of each other, it means we've done something wrong. But notice the bottom equation says x is equal to 1 plus 2y. So any vector where the top entry is equal to 1 plus 2 times the bottom entry is going to be a generalized eigenvector as long as we don't pick the 0 vector. So for example, any vector of this form for any value of s, as long as we don't get the 0 vector, which as you can see is never going to happen. So really, for the generalized eigenvectors, for any parameter value of s, this is going to give us a generalized eigenvector. In particular, if we pick an easy choice, say s is equal to 0, we get 1, 0 as the generalized eigenvector. And so the general solution is x of t is equal to c1 e to the t, because lambda is equal to 1, so e to the lambda t is just e to the t, times the eigenvector 2, 1 plus C2 e to the t times the eigenvector t1 plus the generalized eigenvector 1, 0. And again, to get this formula, you can either look back at the class notes or look at the class video or read the book. But that's the formula that we're using, where W is the generalized eigenvector, and the generalized eigenvector is any non-zero solution to that equation.